The last part of Chapter 9 dealt with hybridization, which is basically our way of describing and understanding the observed geometry and bonding interactions for something like carbon. Right, and where this comes in is, we started off by looking at direct orbital overlap. So for example, we looked at the formation of something like hydrogen, H2, and we can understand the formation of hydrogen by thinking of direct orbital overlap. You have your 1s orbital from one hydrogen that contains an electron. You have your other s orbital from another hydrogen that contains also a 1s electron, right? Hydrogen is 1s1, 1s1. There's our direct orbital overlap. We're sharing those electrons, right? There's my hydrogen-hydrogen single bond. So sure, there's my linear geometry I see in H2 that explains the observed geometry I see in H2. But what we can't explain, for example, is something like carbon. We know carbon can form 4 bonds, and we know carbon also will be of a tetrahedral geometry, which is 109.5 degree bond angles. So how do I explain that? If I'm only working with s and p orbitals, right, each of these p orbitals is basically 90 degrees from the other. We've got one in the x-plane, the y-plane, and the z-plane. If they're overlapping with an s orbital, how do I get 109.5 geometry? And the other issue we have with carbon is helium 2s2, 2p2. And if I look at that, right, here's my s orbital, and here are my 2p orbitals. So here's 2s, here's 2p. Got 2 electrons there, right? 1, 2, and I've got 2 electrons here, 1, 2. Well, in order to form a bond, we need each orbital to at least provide 1 electron. So looking at the electron configuration of carbon, you would think carbon could only form 2 bonds. There are 2 p orbitals where there's 1 electron each, so there are only 2 p orbitals where I could accept 1 electron each. So that being said, how does carbon form 4 bonds? If I can only accept 2 electrons, I only have 2 p orbitals that each have 1 electron. That would kind of make it harder for me to form 2 bonds. So let's take a look at how we explain carbon forming 4 bonds total. Right, here's my configuration of carbon, my normal configuration of carbon. 1, 2, 1, 2, 1, 2. I need to generate 4 orbitals that each have 1 electron. And then that would allow me to form 4 different bonds where each orbital is giving 1 electron, or able to share 1 electron. So what happens if I took and promoted an electron? I promoted this electron from the 2s orbital, and I promoted it up into the 2p orbital. That would give me a configuration like this. And now, yes, I would have 4 orbitals, each containing 1 electron, a 2s and a 2p orbital. The only problem with that is, or one of the problems with that, is if we look over here in energy. What this means is not each of these orbitals are of the same energy. And so this would create a problem in that the 4 bonds we could form would not be of the same energy because the bonds are originating from different orbitals. So the s and p orbitals are not of the same energy. That would make it difficult for us to understand when I look at something like carbon that forms 4 bonds, right? All 4 of those bonds in the case of methane, for example, CH4, all 4 of those bonds are identical. So they must come from 4 identical orbitals. That's not what we have here. I would have 1 coming from an s orbital and then 3 coming from a p orbital that are of different energy. So we still haven't decided, or still haven't figured out how we can explain carbon forming 4 bonds. And that's where our hybrid orbitals come in. Our hybrid orbitals basically allow us to explain carbon forming 4 bonds from 4 identical orbitals. So if we go back to the configuration of carbon again, helium 2s2, 2p2. So here's my 2s orbital. Here are my 2p orbitals. I have 1, 2, 1, 2 electrons. So hybridization is essentially you're taking those orbitals and you're going to mix them together. And for each, these are my atomic orbitals. And for each of the atomic orbitals you mix in, you're going to get one hybrid orbital out. So we take those 4 orbitals and we mix them together. And so I'm going to take and mix my 2s orbital plus each of the p orbitals. So I'd have 2px and 2py and 2pz orbital. I mix them all together. And now I'm going to get out 4 hybrid orbitals. So I mix 4 atomic orbitals my 2s plus the 2px, each of the 2p orbitals essentially, 2py and 2pz, to obtain 4 hybrid orbitals that are all sp3. So these are no longer s orbitals, they're no longer p orbitals, they are sp3 orbitals. And all that means is for an sp3 orbital, we can think of it as, right, what is that orbital composed of? That orbital is approximately 25% an s orbital and 75% a p orbital. And where did that come from, right? I mixed one s orbital with 3 different p orbitals. Now I can go back and reassign the electrons. I have 4 electrons total, 1, 2, 3, 4. Now I can explain carbon forming 4 bonds because I have 4 hybrid orbitals that each contain 1 electron. Now I have 4 hybrid orbitals that can each accept an electron, and their important thing is they're all identical orbitals now. Previously I had an s and 3 p orbitals. Now I have 4 identical orbitals that are each sp3. And that's what we see here. I've taken those 4 atomic orbitals, I've blended them together. Here's my s orbital, and I've mixed that with my p orbitals. I blend all of those together, and now that I have 4 electron domains and 4 hybrid orbitals, I get my tetrahedral geometry when I have those 4 electron domains. So now I have a way of explaining carbon being able to form 4 bonds. It's not with s and p orbitals, it's with my sp3 hybrid orbitals. And so that original explanation for carbon forming 4 bonds by promoting an electron from the 2s orbital up to the 2p orbital, right? We said that did not work because that would create orbitals of different energy that would be using to form the bonds, and that's not what we observe. So instead, we observe this configuration of carbon. 1, 2, 3, 4 for my 4 valence electrons that I have for carbon. The important thing is, if we notice again, is our energy, right? My energy is over here. My hybrid orbitals, my hybrid sp3 orbitals, right, they are higher in energy than an s orbital. They are lower in energy than a p orbital because I've blended those orbitals together. I've mixed those orbitals together to make 4 identical orbitals. But what's important is that all 4 of those orbitals now are identical energy. They each contain 1 electron, which means they can each share, accept 1 electron to form a covalent bond. So if we look back at the methane example, right, carbon forming 4 bonds, well, hydrogen, and I'll put hydrogen in blue here just to differentiate the electrons from hydrogen. Hydrogen is 1s1, right? Hydrogen has an s orbital with 1 electron in it. So if I bring in 4 separate hydrogens, each containing 1 electron in their s orbital, they'll overlap with the hybrid sp3 orbital to form 1, 2, 3, 4 covalent bonds. And that's what we see in something like methane with CH4. I can form 4 carbon-hydrogen single bonds by the overlap of the sp3 hybrid orbitals on carbon and the s orbital on hydrogen, the atomic s orbital on hydrogen. And so why this is important is because now if I know the geometry, you should also know the hybridization, right? And the important thing that allowed us to figure that out was for each atomic orbital that we mix, we're going to get one hybrid orbital out. I'll write that down. For each atomic orbital mixed, we obtain one hybrid orbital. So where did we start? We started with linear. If I'm linear, I have 2 electron domains. So how I would need 2 hybrid orbital domains. How do I generate 2 hybrid orbitals? Well, I'd have to mix together 2 atomic orbitals. So if I mix together an s and a p orbital, right, I would obtain 2 hybrid orbitals that are both sp. And that's what I see. If I'm linear geometry, I would be sp hybridized. If I'm trigonal planar geometry, I need 3 electron domains. I need 3 hybrid orbitals, so I'd have to mix together 3 atomic orbitals, s, plus 2 different p orbitals now, and that would give me 3 hybrid orbitals that are all sp2. So approximately 33%, right, of an s orbital and about 66% of a p orbital. We've already went over carbon and sp3, but again, if I'm tetrahedral geometry, I need 4 electron domains. So to obtain that, I need 4 hybrid orbitals. I'd mix together an s orbital and 3 p orbitals, and out of that, I would get 4 hybrid sp3 orbitals. We've also talked about trigonal bipyramidal and octahedral geometry, right? We know some things have 5 and 6 electron domains. The only problem is we've used our s orbital, we've used all of our p orbitals. I only have 3 p orbitals, so how would I explain 5 or 6 bonding interactions, 5 or 6 electron domains? Well, the only orbital we have left are our d orbitals. So if I need trigonal planar or trigonal bipyramidal geometry, I would need 5 electron domains. To obtain 5 electron domains, I would have to mix together 5 atomic orbitals. So there's 4 s, 3 different p orbitals, and now I'd have to mix in a d orbital, and that would give me 5 hybrid sp3d orbitals. So now each of those orbitals is an sp3d orbital. They are all hybrid orbitals. If I need 6 electron domains, I'd have to just mix in 1 more d orbital, so it would be s plus 3 p orbitals and 2 d orbitals. That would create 6 hybrid orbitals that are all sp3d2. And now we've got the hybridization of all the different geometries that we looked at. Linear, sp, trigonal planar, sp2, tetrahedral, sp3, trigonal bipyramidal, sp3d, and then octahedral, sp3d2. So now if you know the geometry, you should automatically know the hybridization as well. So what are the hybrid orbitals that we're using to form our bonding interactions? What are the orbitals our lone pair electrons are sitting in? And so a step-by-step process to figure this out, right? Number 1, we're going to draw our Lewis structure. Based on the Lewis structure, we're going to determine how many electron domains do I have. And then after my electron domains, based on that, what would the hybridization need to be? So our Lewis structure for water, right? I've got oxygen that has 6 electrons. I've got 2 hydrogens. So 2 electrons total. That's 8 electrons I have to assign. 4 are bonding and 2 are non-bonding. So I have 4 electron domains. Based on those 4 electron domains, my electron domain geometry would be tetrahedral. And because I'm tetrahedral, right, I would need 4 hybrid orbitals. To generate 4 hybrid orbitals, I'd have to mix together 4 atomic orbitals, so S plus 3 different p orbitals, right? I would need to be sp3 hybridized for water that has a tetrahedral electron domain geometry. So here's water. Here's my electron configuration of water. We're not going to use the 2s and the 2p orbitals. We're going to hybridize those orbitals. We're going to mix those orbitals together. Going to blend those orbitals together. Here's the electrons I have. I still have 6 valence electrons. So 1, 2, 3, 4, 5, and 6. And this is important because what this means is that each of these lone pair electrons, right, in water, I have 2 lone pairs of electrons that sit on the oxygen. Each of those lone pair electrons are in a hybrid sp3 orbital. And then the other important thing is I've got 2 other electrons that are each also in an sp3 hybrid orbital. So how do I explain the bonding interaction of water? Right, again, here comes hydrogen. Hydrogen is 1s1. Here's my s orbital of hydrogen with its 1 electron. And that can overlap with this hybrid orbital and overlap with this hybrid orbital to make the 2 bonding interactions we observe in water. So my lone pair electrons are in hybrid sp3 orbitals, and my 2 bonding interactions occur between hybrid sp3 orbitals on oxygen and the atomic s orbital on hydrogen. And that's exactly how I would describe this, right? So in water, right, there are 2 lone pair electrons on oxygen in hybrid sp3 orbitals. And then I have oxygen-hydrogen bonds formed between or formed by the overlap of hybrid sp3 orbitals on oxygen and atomic s orbitals on hydrogen. So here's our sp3, 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 and then here would be our atomic s orbitals from the hydrogen. Hydrogen will never hybridize. Hydrogen only ever has an s orbital, so we'll only use the s orbital from hydrogen, but this explains our geometry. This explains the 2 lone pairs of electrons. They're in identical hybrid orbitals, and then my bonding interactions are also between the hybrid sp3 orbitals on oxygen and the s orbitals on hydrogen.